Hello. Um, this is the second video that I'm making for chapter 8. I'm gonna review chapter 8 for a while, and then I'm gonna do some problems from Newton Alta. And remember, chapters 7 and 8 are the sections that are in the next test. So after this, you should be able to finish the homework in Newton Alta and take the test. All right, so let's start. And first, let me get rid of my video. I don't think we need it. So let me get rid of that. All right, so this chapter is about confidence interval. So now I assume that you read the notes already, so I'm going to go over the most important concepts in this chapter. So what we are going to do in this chapter is very simple. Suppose we don't know a parameter from a population. Now the question is, how do we find out? And we know in statistics, we take a sample to find out, to estimate the value of the parameter. So suppose we don't know the average height of our college students. So the way we find it is we take a sample and then we find the average of that sample, and that would be a point estimate for the average height of the population of all the students in our college. But of course the question is, how do we know that that average is actually the average that we're looking for? Well, that's what this chapter is all about. So first, of course, we are going to learn how to find the point estimate for the parameter. That's very easy. Just take a sample and then calculate whatever it is that you're estimating. If you're estimating the mean, then we find the x bar. If you're estimating the proportion, then we find the proportion. So that's what this chapter is all about. Okay? So, and we have done 7 chapters just to be ready to prepare to do inferential statistics. And this is the first chapter that we actually start doing some inferential statistics. We've been collecting data, organizing data, talk about analyzing data, but before we can actually make any decisions based on data, we have to do some inferential statistics. So here is the first chapter that we're going to do that. All right, so here's an example. Suppose we're trying to figure out the proportion in some population. So in this case, is you're trying to determine the percentage of times you make a basketball when shooting a basketball. So the population is basically, all the different times that you try to make a basket. Now, out of all of those times in your lifetime, how many of them did you make and how many of them you didn't make? Well, we don't know that because you haven't done a lot of shooting yet. So what we do is we basically take a sample. So what is a sample? Well, you throw some basketballs and see how many of them you make. So you do maybe 50 of them and see how many out of 50 you make. Suppose you make only 2 of them. Well, that makes it 4%. So that's the, when you take 50, when you do it 50 times, so let's say you do it 50 times, so the sample size is 50, and you only do 2 out of 50, then this percentage is just 0.04, right? So it's 4%. So we say that 4% is a point estimate for the actual proportion, which we don't know. Okay? So that's the proportion. Now, what if we want to know the average cost of a 2-bedroom apartment in Houston area. Well, we go to Houston area and we sample, because it's very hard to go to every apartment complex in the Houston metropolitan area and figure out how much the 2-bedroom apartment rent is. So what we do, we take a sample. Let's say we take a sample of 100, and then we average the rents for 2-bedroom. And what we find, of course, is going to be X bar. And then X bar is a point estimate for that mu that is unknown. Okay? All right. Now, of course, when we find a point estimate, how do we know, for example, that this X bar that we find is actually equal to that mu that we're looking for? Well, we don't know. And this chapter tells us that we can represent this number. So we're not going to go say, okay, we found mu. Mu is exactly what we found. That's not true. We don't know that. So in this chapter, what we do, we are going to represent that. We're going to report that to people with an interval. And that interval is basically plus and minus some error. So we accept that we could be wrong, but by how much? And that would be the error we accept. So we're going to say we are only 95% confident that the mean that you're looking for is in this interval. And I mean interval means what? Means X bar plus error and then X bar minus error, right? All right, so that's what we want to do in this chapter. So we have a point estimate, which is the number that we calculate from the sample. And then we have certain amount of error that we accept. So we're going to add and subtract that error and then present that interval as confidence interval. That's what we want to do in this chapter. So now, if the population, suppose here, the population is the population of basically number of songs that the consumer downloads from every month from iTunes. Now, we don't know what the average number of songs that consumers download is. So, but suppose we know the standard deviation of the population. Now, later we're going to see that we don't normally know the standard deviation either, but for now, we assume that we do. So we do know the standard deviation of the population of number of songs that people download from iTunes. Now the question is, what is the mean? Well, we don't know that. So how do we find out? We take a sample. They take a sample of certain size, let's say 100. So we take a sample of 100, and then we calculate X bar to be 2. Now, the question is the average number of songs that consumers download from iTunes equals to 2? Well, we know for sure that's not the case. But we can use the central limit theorem and say, okay, what if we take another sample of 100 and we find another mean? So let's say this is X bar 2 and that was X bar 1. And this X bar 2 is maybe 1.9. Or maybe we do it again and we find another X bar. Now we know from previous chapter that the X bars make a distribution that is normally distributed. What is the mean of the distribution? The mean of the X bars is the same as the mean of the population. And the standard deviation of the X bars, is the standard deviation of the population divided by square root of n. And we know that already is here. Okay, now, so we're not sure 100% that 2 is actually the mean that we're looking for, but we could be 95% sure. Remember empirical rule? So by empirical rule, we know that in a symmetric distribution, 95% of the X bars are within 2 standard deviation of the mean. Now we assume, if we assume that 2 that we find is actually the mean, if we make that assumption, then we say, okay, if this is 2 in the middle, then how much can we be off? Well, we could be off by 2 standard deviations to the right and 2 standard deviations to the left. But what is the standard deviation of X bars? Well, the standard deviation of X bars is this. Now remember, we assumed that the standard deviation of the population is 1, and I put 2 here. I have to fix that. The standard deviation is 1. So if the standard deviation is 1, now remember it was 1, right? It's just the typo that is 2. I fixed it. So if the mean is 2 and the standard deviation is 1, standard deviation of X bars is not 1. Standard deviation of X bars is 1 divided by square root of n, which is in this case, remember, 100. So 1 over square root of 100 is 0.1. So 0.1 is the standard deviation of the X bars. So we have to go to the right of 2, right? 0.2 of these, 2 times 0.1, and we have to go to the left of it, 2 times 0.1. So that puts us at 1.8 and 2.2. So that means we can actually be 95% confident that the real mean that we're looking for, which is this right there, is between 1.8 and 2.2. And that's how we're going to report this. All right, so that's the idea of confidence interval. Now remember, in this case, we do know the standard deviation of the population. In the next section, we're going to see what we can do if we don't. All right, so now we say that we are 95% confident that the unknown population mean number of songs downloaded from iTunes per month is between 1.8 and 2.8. Okay, so, and we call that interval, we call this interval the 95% confidence interval. All right, so so notice that we start with a population and we take samples of certain size n, and then we calculate X bar. Now we assume that if we keep doing this, then these X bars make a distribution that is normally distributed, approximately normally distributed, with the mean equal to the mean of the population, and the standard deviation of the population divided by square root of n. So now, based on that assumption, then we say that if we want to be certain percentage confident, we call it confidence interval, confidence level. So the confidence level depends on how confident we want to be. So if we want to be 95% confident, then we're going to have to go to the right and to the left of the X bar with certain error. Now, error here is what? Well, the error is nothing but what? But certain number of standard deviations. We know standard deviation is that for X bars. Certain number of standard deviations. We're going to call that Z sub C, or we can call it Z sub alpha over 2. I'm going to see why we call it alpha over 2 in a second. So, certain number of standard deviations to the right and certain number of standard deviations to the left of the mu. That means X bar. So E is the error bound for the mean. We could just call it E. Now, so again, notice that we have a population that the samples come from. Then we have the population of x bars. So this is x, this is x bars. And then we can convert the population of x bars to z's. So how do we get z out of x bar? Well, we have a formula for that. It's right here. If x bar minus its mu divided by its standard deviation. So that's the z. So this x bar converts to that z. So this z is actually the number that has to be between this number and this number. Now, I said I use empirical rule to say that we can go 2 standard deviations to the right and left of the mean, but we don't have to use confidence. We don't have to use interval empirical rule. We can use just z distribution. We can find out from chapter 6, we can find out what are 2 numbers on standard normal distribution that have 95% of the data in the middle of them. And if we do that with inverse normal, we can easily see that that number is negative 1.96, and this number right here is positive 1.96. So the 2 numbers on the z, on the standard normal distributions that have 95% in between, are negative 1.96 and 1.96. That means if you go to the right, not 2 standard deviations, but 1.96 standard deviations, then you can capture 95% of any standard normal distribution. Now, if you apply that to any normal distribution, then all you have to do is take your number of standard deviations, which we call it z alpha over 2, to be 1.96. So if we have a situation that we have an x bar and we want to represent that as an interval, well, we can add and subtract how many standard deviations? That many. If we want to be 95% confident. If we want to be 99% confident, then these numbers change. If we want to be 90% confident, then these numbers change. But in either case, once we have this number, we can just multiply that by number of standard deviations, right? So that would be our z, and then multiply it by number of standard deviations. So that would be number of standard deviations to the right and to the left. All right, so here in this formula, we have to do some algebra to figure out the formula. So let me erase this right here quickly. So what we are saying here is that, you see under z here, we assume that the 2 numbers right here are z alpha over 2 negative and z alpha over 2 positive. So this x bar, which we convert to z, has to be between these 2 with what probability? Let's say 95%. So this is the probability that we call confidence level. Now, the area in the tails, the 2 tails, is 1 minus this amount, right? So we call that area in the tails alpha, both together. So alpha is the area in both tails. Now, 1 minus alpha gives you the middle, which is the confidence level. So what we are saying here is that we want this x bar, which is converted to this z, to be between this number and this number with the probability of 95%. So if we write that and then isolate mu in the middle, we're going to get this formula. Now you don't have to actually derive this or actually prove this either. You just have to be able to use it. But this is just in case you want to know where we get this formula, that's where it comes from. With a lot of algebra, we can isolate mu in the middle. So we say the real mu that we're looking for is between x bar that we find from the sample plus some error and x bar minus some error. And that's how we build confidence interval. All right, so that's called margin of error, right? So margin of error is what we add and subtract. So the alpha, again, is the area in the tails. So if we have alpha amount for both tails, then for each of them we have alpha over 2. And these numbers are called z alpha over 2, right? One of them is negative, one of them is positive. All right. So let's do some examples from. Before we do some examples from Newton Alta, let's look at the ideas that I talked about. How do we know that what are two numbers that have 90% between them in the middle, 90% of the data on standard normal distribution is between what two numbers? Now, to find that, we use a calculator, of course, and we use what? We use inverse normal, right? So if we want to know what this number is, we go to distributions, and then we find inverse normal. Then how much area do we want to be to the left of this? Well, if there is 90% in the middle, then there is 10% in the tails, so each of them takes 5%. So how much is to the left of that? 5%. So we put 5% in decimal. And the mean and standard deviation for standard normal distribution is 0 and 1. And you see it's negative 1.645. If I want to find this number, then I do the same thing. I'm going to get the entry back. But this time, area to the left is not 5%, is 90% plus 5%. So how much area is to the left of this number? 95%. So I'm going to make that 9.95. And you see I get 1.645. And if I want to know the numbers that have 90% in the middle, then I do the same thing except 95%. Well, if it's 95% in the middle, then how much is left for the tails? 5%. What's 5 divided by 2? 2.5%. So each tail gets 2.5%. Now, 2.5% in decimal is 0.025. So how do I find this number right here? Well, to find this number right here, oops, I went back. So to find this number right here, all I do is, again, to get the entry back, inverse normal, and I'm going to change that to, how much is to the left here? How much is to the left? 0.025, and I have to redo this because I wrote over them. That's okay. There. Oops. There's something in the end tag. Oh, I put 2 decimal points. So negative 1.96 right there. And how do I find this one? Well, how much is to the left of this? Well, that's 0.95 plus 0.025. I could just put it like that. So I'm going to get the entry back. I know what I'm going to do. I'm going to do 0.95 plus 0.025. That's how much is to the left. I don't even do the calculations by hand. And then 0 and 1 are the mean and the standard deviation. 1.956. Okay, so forth. So that's how you find that z that we're looking for, which is the z alpha over 2, right? So z score for the confidence interval. For every confidence interval, we have a z-score. Now, these three numbers are famous, so you should memorize them. 1.645 for 90%, 1.96 for 95%, and 2.58 for 99%. Okay? So here's an example. Suppose the scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives a mean of 68. Find a confidence interval estimate for the population mean exam score. Well, we want to be 90% confident. So basically what we have to do is we have to take x bar and add and subtract 0 alpha over 2 times sigma over square root of n. So what is our x bar here? 68. Plus and minus. What is our z? Well, remember for z for 90% was 1.645. And then multiply that by, what's the standard deviation of the population? 3. And what's the sample size? 36. That's it. That number gives us the answer. So you multiply all that, you're going to end up with we're going to end up with 68 plus and minus 1.645 times 3 over square root of 36 is 6, so that's just 1/2. That's 0.5 times that. So 68 plus and minus this times 0.5. And that would be right here. So there. 1.645 times 3 over square root of 36. So it's 0.8225. So that's the error. So we're going to take this and add it to 68 and take this and subtract it from 68 and we get the interval. Now we can easily do this with a calculator. So how do we use a calculator with this? Well, we are going to go to stat and go to tests, and then we are going to go to the one that says z interval. You see it says z interval number 7. Pick that one. And now the question is, do we have data or do we have statistics? Now statistics is of course the x bars and everything else we calculate from the sample, and data would be if you're given the raw data. Okay, so we have a statistics here, so we're going to pick a statistics. And then what is the sigma of the population? Well, remember the sigma of the population was 3, so we put 3 there. And what is the x bar from the sample? Then remember that was 68. And what's the sample size? 36. And what is the confidence level that we want? 0.90, right? And with the 0.90, we are going to get that. Is that the numbers that we have there? Yes. 67.178 and 68.822. See, we got the interval right there. Make sense? I think it makes a lot of sense. Alright, so that's how we do it with the calculator, and there are steps in the notes here how to do it with the calculator. Now, this one I let you do yourself. We're going to do another one that has raw data. But this one has raw data. We are given raw data. We are not given the statistic. So it says find a 98% confidence interval for the true population mean of specific absorption rates for cell phones, and we are given the data here. So what you have to do, you have to put all of these in your calculator in L1. So you put all of them in L1, and then you can actually do calculations. So you put all of them in L1, and you can calculate this. So I'll let you do this yourself. So you go to the same place in calculator, stat edit, and put all of these numbers. It doesn't matter in what order, you just have to put all of them in L1. And then you run that test again, the Z interval, and you can do it. So here, if we do that, you're going to find out that the error here would be this, because we know the standard deviation of the population is given here, 0.337. So all we have to do this problem is to put that divided by square root of 30, because notice there are 30 of these data points, and then multiply that by 2.326. Now, 2.326 comes from 98% confident. How do we get that? Well, we can go to second distribution, inverse normal. Now, what we want is, we want a number that has 98, we want two numbers that have 98% in the middle. Now, if it's 98% in the middle, then there's 2% left. Each tail takes 1%. So if you want to find this right here, all you have to do is just put 1% to the left, which is 0.01. And then comma 0, comma 1. And that gives you negative 2.326, which is that number right here. So, of course, we don't use negative or positive, we just use the absolute value of it, because we are going to add and subtract this number. So we doesn't matter the sign. Okay, so we get that, and that would be the error. Now, we're going to have to find the mean of these numbers using, the one variable stat, and then put it in this formula and add and subtract right here. So this is the x bar. So to find the x bar, of course, we don't have to do all that. All that we can do it with calculator. So if you do it with a calculator, in this case, you're going to put all the data in L1, and then you open your Z interval here. So that's what I was talking about, was if you wanted to do it by hand. Now, if you want to do it completely with the calculator, you go to stat, you go to tests, and you go to Z interval, and this time you pick data and press enter. And then you put all your numbers in L1, and then fill in the rest of this. For sigma, you put 0.337, as I have it here. And then for confidence level, you put 98%. And then you run this, and it gives you the interval. See? It's very easy. All you have to do is to put the data in L1, and then run this Z interval. All right. Now the question is, what if we actually want to do a study, and we want to see what happens if we increase the sample size, or we change the Z. That means our confidence, right? Remember, Z has to do with the confidence. So if you want to be 99% confident, your Z would be bigger than if you want to be, let's say, 90% confident. Then your Z would be smaller, right? I put it in the wrong place, but so let me erase that. So you see, if you want to be 90% confident, your Z would be smaller than 95%. If you want to be 99% confident, then your Z would be a little bit bigger. So as if you want to be 0 confident, then this is just 0. So you don't have any error. You just represent it, with X bar. You say, okay, my X bar is mu. But of course, that's not true. You can only say that if you're 0% confident in what you're saying. All right, if you want to be 100% confident, then you give your interval as negative infinity to infinity, because your Z would be infinity, right? It goes forever this way. So if you want to be more confident, then your Z would be bigger. That means your interval would be bigger. Now, notice that sample size is in the denominator. So if you increase the sample size, then your interval, your error gets smaller because it's in the denominator. So if you have a bigger sample size, you have a smaller error. All right. So working backwards to find the error bound or the sample mean. Well, if you're given an interval, so if you're already given an interval, let's say I give you that interval is between 2 and 8. Well, if you know 2 and 8, then the middle of this number would be 2 plus 8 divided by 2, right? And that would be 5, because 2 plus 8 is 10 divided by 2 is 5. So 5 is actually mu. Mu, not mu, but X bar I meant. X bar. Now, what is the error here? Well, the error would be the distance from the middle to 8 or from the middle to 2. So all we have to do to find the error is to subtract them and divide by 2. So 8 minus 2 is 6, divided by 2 is 3. So if somebody gives you an interval of 2 to 8, then we know that the X bar is 5 and the error is 3. So 5 is in the middle. You go to the right 3, and you go to the left 3, you get to 2 and 8. To 2 and 8. Okay? So given an interval, you can easily find the error bound and the mean. Now, what if you want to do a study and you don't know what n is supposed to be, which is the sample size? Well, we know that the error here, just think of this as just one number, right? That's just one number. This is just one number. So if the error equals to z times sigma over square root of n, then we can isolate z with a little algebra. If you square both sides, we can isolate n, right? And now we have a formula for n. Remember, this whole thing is just one number. That's the error in decimal. So if you want to be 3% confident, 3% error, if you want to have 3% error, then you put 0.03 here. So if you do that, then you can find out what the sample size is supposed to be. So let's do an example. It says a population standard deviation for the age of Foothill College students is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean, then how many randomly selected football students should be, college students, Foothill College students should be in there, should be in the sample? Well, we're going to put it in that formula, right? Remember that Z right there is the Z for 95%, which is 1.96. If you want to be 95% confident under standard normal, the two numbers that have 95% in the middle are negative 1.96 and 1.96. So that takes care of that Z. Has to be 1.96. Why? Because we want to be 95% confident. Now, the sigma, of course, is given, which is the standard deviation of the population. We put it there. And then the error, we want to be within 2 years. So 2 years is the error, and the unit is years. So 2 years, we put it there. Now notice the error is not given in percentage form, it's just given in the raw form, 2 units, and unit here is a year. So we put a 2 there, and then we do the calculation with the calculator, we get 216.09. Well, obviously you cannot take 216.09 samples. I mean, is not practical. Can't do that. So we always round up. Always round up to the next integer. So 217 is the right number for n. Alright, so if we want to do this study, we should have at least 217 students in order for us to be able to find a number we can represent as an interval to be 95% confident that our error will not go over 2 years. Now, you have seen in editorials or in the news, they say this person has 50% approval rating plus and minus 3%. Well, plus and minus 3% is the error. Alright, so there is a good video clip you should watch for this section. And then, so I'm gonna now go to Newton Alta and do some problems from Newton Alta, a few problems, and then we come back and talk about the situation when we don't know the standard deviation of the population. So let me go to Newton Alta and do some problems from, oops, where'd they go? There you go. So here's Newton Alta. So I'm going to go to this section here, close it and go back. So let's go to this section here and do a few problems. It says the average number of chips per bag from potato chips available at a supermarket is unknown. So the average number of chips you get per bag is unknown. A random sample of potato chip bags from the supermarket yields a sample mean of 250.6. Now, assume the sampling distribution of the mean has a standard deviation of 18.9 chips. So we are given a standard deviation of the sampling distribution of the X bars is 18.9. Use empirical rule to construct a 99.7% confidence interval for the true population mean number of potato chips. Now, so let's first of all get this answer and then see how we can do it quickly, and then we do another one ourselves. So here we are using confidence, we are using empirical rule, and so 99.7% by according to empirical rule is 3 standard deviations. So remember, 95% is within 2 standard deviation, 68% is within 1 standard deviation, and 99.7% is within 3 standard deviations. So all we have to do, we have to go to 3 standard deviations to the right and to the left of the mean. And in this example, you don't have to find any z because z is given, z is 3, right? So we're not using normal distribution here, we are using empirical rule. 3 standard deviations to the right and 3 standard deviations to the left. So all you have to do is take the mean that is given, 250.6, and add 3 standard deviations, which is 18.9, to it, and then subtract 3 standard deviations from it, and you get the interval. Alright, so that was empirical rule. Let's say if this is empirical rule, no, it says construct a confidence interval for the mean. So let's use the calculator quickly here. So what I'm going to do, I'm going to use, I'm going to do z interval, but I'm going to do with the statistics because we are given a statistics. So I'm going to go to stat tests, and I'm going to go to Z interval and pick a statistics. Pick a statistics and go down to, okay, what is my sigma, my standard deviation of the population? So it says a contest for the free tickets, a number of, in a reviewing of the results, a random sample of guesses, contestants regulator found the mean guess to be that with a margin of error of that. Construct a confidence interval. Okay, so we don't even need a calculator because we're not given the standard deviation. We are given actually the mean, and we are given the margin of error. So we just have to add and subtract that to it, and we are done. So this is even easier than I thought. So it's 136 plus that and minus that, because that is a complete error section, right? Let me make sure we are on the same page here. So let me get this so I can write on it. So what we are saying is that the confidence is given by this formula, but here we are told that this whole thing is 13 and this right here is 136. So we just have to add and subtract to get it. So let's do that. So 136 plus 13 and 136 minus 13 is going to be what? The interval would be 123 to 149, right? All right, it says the heights of American women are normally distributed for a random sample of American women. The confidence interval is generated. Find the margin of error. Okay, well, we talked about this. Margin of error would be the difference between these two divided by 2. So it would be 67.4 minus 61.8, and then divide that by 2, right? So 2.8 is the margin of error, right? All right. So the average weight of population of female calico cats is unknown. Random sample of female cats selected from the population yields a sample mean of that. Assume the sampling distribution of the mean has a standard deviation of that. Use the empirical rule, construct a 68%. Okay, so 68% would be one standard deviation to the right and to the left of 10.1. So that would be one standard deviations to the right and one standard deviations to the left. So one of these we add and subtract and we get that. So 68%, we are 68% confident that the average weight of this kind of cat is between 8.5 and 11.7. All right. Now, again, this is similar margin of error, so I'm going to skip it. You can do that. And what are we supposed to find? It says construct a confidence interval for the proportion of a school board members that plan to vote no on the issue. So a random sample of a school board members in a particular school. The proportion of school board members who plan to vote no on making school days longer to make up for snow days is 0.59 with a margin of error of 0.03. Now, we don't have to know the proportion section in this chapter yet, because this is we don't know how to find the error for proportion yet. We're going to learn that. But here we don't have to, because we are given the margin of error. So all we have to do is just add, right? So we just have to add and subtract and we get the numbers. this is about proportion, but margin of error is given. So we just add it and subtract the margin of error and we get the answer. All right, let's do another one. What is the sample proportion? Well, sample proportion would be if you divide number of successes divided by, well, sample proportion, we don't have number of successes and sample size, but we have the interval. So basically, if this interval is created by adding and subtracting error to p prime, then p prime has to be in the middle. So basically, we add them and divide by 2, right? So if you add and divide by 2, what do we get? We get 0.09 and add it to 0.15 and then divide by 2, we get 0.12. All right, again, the same thing here. I'm just gonna move on. Looks like so again, using empirical rule, the same thing. One standard deviation to the left and right. The same thing. So one standard deviation to the right and left. Okay, so we're given an interval here. It says the heights of American women are normally distributed. If a random sample of American women is taken and the confidence interval is given by that, then what is the sample mean? Well, the sample mean is the number in the middle. So that would be, of course, 68, 63 something. You add them and divide by 2. All right, so I think we got this under control, this section. So now what happens if the population standard deviation is not given, that means is unknown, then we're going to have to use a different distribution. So what I'm going to do for this section, I'm going to create a second part of this video and do it then. I'm going to do another one which includes this and the next section. Okay, so until next video, I see you in the next video. Okay, all right, that's